Hi, in this particular example, I'm going to show you how to completely do a full truss analysis, including finding all the forces in the bars. What I mean by that is, I will help you figure out how to calculate the forces in every bar in this thing. The black lines I'm drawing shows you all the bars, and I will show you how to systematically calculate the forces in all the bars. The process is the following. We first find the reaction forces at the points A and H. That's A, that's H, so we'll find the reaction forces. Then we'll go joint by joint and we'll draw the free body diagram of each joint. And as soon as each of the joints I find the free body diagram, then we will be able to use Newton's laws and the equations of equilibrium to find out what the forces in each of the bars are. This is a very tedious but a very straightforward procedure. So I want you to follow. This involves a lot of geometry, so be ready to do some trig. So get your calculators out, and what I want you to do is, as you see this, you should try and follow. The first step in the process is to draw a free body diagram, which I'm going to do beside the original figure. So here's the free body diagram. So here's the base, AH, and then the rest of the truss looks something like this. The free body diagram is not that great, but you get the picture. So that's 6 kilonewtons, that's another 6 kilonewtons, and that's another 6 kilonewtons. There's 3 kilonewtons here, there's 3 kilonewtons there. My coordinate system is out here. And you can notice that the truss is extremely symmetric. What I mean by that is the left hand side, A, C, E, D, B, looks very much similar, like a mirror image of the right hand side, D, E, G, H, F. So whatever happens on one side will happen on the other, and we will exploit this symmetry quite a lot to figure out the forces in this bar in a very straightforward manner. All the trusses that you guys have built have the same kind of symmetry, so you will be able to exploit the same kind of reasoning to simplify your calculations. The more symmetric it is, the easier it is. Now I have not completed the free body diagram. There's a force AY here because that's the roller, and there's a force HY and HX. In this particular case, I'm not going to draw a complete I'm not going to draw a complete force table and all of that. By now you're very familiar with it. So what I'm going to do is I'm going to simply do a very simple setup where I'm going to sum all the forces. So I'm going to I'm going to sum all the forces in the x direction, and that will give me hx equal to 0 because that's the only force in the x direction. Then I'm going to sum all the forces in the y direction, and that will give me, let's see, ay plus hy minus 3 plus 6, 9, 9 plus 6, 15, 15 plus 6, 24, 6, 15, 24, 27. Let's see. 1, 2, 3, 18 plus 6, 18 plus 6, 24. So how am I getting 6 plus 3, 9. 6 plus 3, 9, 9 plus 6, 15, 15 plus 6, 21, 21 plus 3, 24. So I got 24 kilonewtons here. That's 0. We might guess by looking at this free body diagram and looking at the symmetry that if whatever happens at A happens at H, Hy and Ay will be the same. In fact, you will get Hy equal to Ay equal to 6, as you will see when I sum all the moments. If I sum all the moments about the point A, I will get Hy times 4 plus 4, 8 plus 4, 12 plus 4, 16 minus 6 times 4, 24, 6 times 8, 48, 6 times 12, 70, 72, and then 3 times 18. And if you solve for Hy, this will give me immediately Hy equal to 12 kilonewtons, and then AY equals 12 kilonewtons. You didn't have to do any of the solution, just by the fact we could just use symmetry to find out that AY must be equal to HY. So in your truss, for example, with 1 pound force, you would have found that the reaction at the joints will be half pound each because of symmetry again. You did not have to do any calculations for that. Now the next thing I want to do is to draw the free body diagram at A. So I'm going to go up here and I'm going to draw a little circle and I'm going to isolate just that circle at A, knowing that the roller joint there I have a force of 12 kilonewtons. So if I draw the free body diagram at A, here's the point A, here's the 12 kilonewtons, that's AY, there's the external applied force of 3 kilonewtons, then there's the force FAC. If you go up here you will see FAC and then FAB. So I'm going to draw this vector and that vector. So I'm going to draw FAB, and to find this angle theta, notice that the triangle ABC looks like this. This is 4, that's 3, so this will be 5, so this angle theta will be tan inverse 3 over 4, which is 36.87 degrees. So this is 36.87 degrees. Couple of things. One, forces always point away from the joint. We are assuming that the bars always pull at the joint. If it turns out that's not the case, then you'll find that the forces will come out to be negative. Not to panic. So it's a pretty simple thing. Now I'm going to set summation of all the forces in the x direction equal to 0. Immediately will give me FAC plus FAB cos 36.87 must be equal to 0, because those are the only two forces in the x direction. Summation of all the forces in the y direction equal to 0 gives me FAB sine 36.87 minus 3 minus 12 equal to 0. So that's A, that's B. So from these two you can see that from B I will get FAB equal to 15 divided by sine 36.87. Sorry, minus 3, my sign is incorrect. So 12, 3, 15, no, that is 9 divided by. So you can see that even I make mistakes when I'm doing this. So be careful when you're doing this. So what I did was a sign error. This was a plus and not a minus. Notice the arrow is pointing up. The arrow for this is pointing down. So FAB is 12 minus 3. So this will be minus 9 divided by sine 36.87. which turns out to be minus 15 kilonewtons. Not only that, you can get FAC will be 12 kilonewtons. Just solve these two equations. The main thing here is drawing this free body diagram. Once you get the free body diagram, it's just like a particle in equilibrium. So every time, the main trick is getting the free body diagram of each particle and being able to do this properly. So what I'm going to do now is I'm going to enter these values onto the truss so that you know where these things are. So this is minus 15 kilonewtons, that's 12 kilonewtons. So what does minus mean? So negative numbers for link forces or the internal forces mean that the bars are pushing against the joints. We don't do anything about it, we don't care actually. Now we have to do the next joint. Now we have two possibilities. So remember, the way we do is we ripple through this thing. So we start out, we'll first figure out all the joints in this triangle, then go to this triangle, then go to that triangle, and keep going all the way through. So we are at the triangle ABC. Now should I go to joint B or joint C? Well, if I go to joint B, you can see that joint B has a lot of different pieces in there. Joint C has only a couple of bars attached to it. So always go for the joint in which there are only two unknown bars. If you go to joint C, for example, this bar we don't know, this bar we don't know. That's where we need to go. So on the other hand, at joint B, we have three unknown bars. So it's better to start with joint C. So I'm going to draw a free body diagram for joint C. What I do is I draw a dotted line. One very key point, once we are done with the external reaction forces, we don't anymore draw just the outline of the whole truss. We actually draw every bar, and when we draw the free body diagram, we show the internal bars. That's how we calculate the internal forces. So remember that. So at joint C now, let's see, there is the joint C, and there is FAC, and we know its value, that was 12 kilonewtons. There is FCE, and then there is FCB. That's it. Those are the only forces. So this is a very easy one. Summation of all the forces in the x direction equal to 0 will immediately give us FCE minus 12 equal to 0. That means FCE equals 12 kilonewtons. Summation of all the forces in the y direction equal to 0 gives me FCB equal to 0 because that's the only force out there. So now I got two more forces. I go up here and I say, okay, this is 12, that's 0. So let's take stock and see where we are. So what I'm going to do is I'm going to redraw this. Of course, I can do all kinds of magic with this particular device. So it's easy for me to redraw these things. You don't have to redraw. This is just a way for me to get this done in a reasonable and efficient way. So here we are. So what do we know now? I'm going to erase all of this so that it becomes more visible. There was the original truss underneath all the stuff that I drew. And let's see, where are we? Well, we figured out that this was minus 15. We figured out this was 12. We figured out this was 12. We figured out that was 0. So now I'm going to go to joint B. So I'm going to draw a little dotted line around joint B. And I'm going to draw these four things. It's bristling with bars. So this is our trickiest joint. And there are lots of angles. So let's draw joint P. And I'm going to draw it fairly large so you can see it well. So there is this force I've drawn it very long so that you can see it far away. This is FAB and this is minus 15 kilonewtons. Notice that I used the same value as I got. The only difference is the difference between joint A and joint B is the force at joint A is this way, the force at joint B is that way. So you can see that they are equal in magnitude and opposite direction. So the force at joint AC will be like this, and the force at joint CA will be like this. So each of them will be equal and opposite like that. So you get an idea of how Newton's third law works in this particular case. I'm actually not telling you the whole truth with regard to Newton's third law here. So what I'm telling you is the truth, nothing but the truth, but not the whole truth. You'll have plenty of time to learn all the details when you take the next level class, statics and dynamics. In this particular case, all you have to remember is whenever you draw those joint forces, the arrows, as long as you point away from the joint, whatever numbers you get, you can just copy down. So there's a force here, but the nice thing is its value is 0. Then there is this force FBD, and then there is this force FBE. So just to make sure you understand what the angles look like, so that's the ball there. So what's this angle? Theta. Well, I'm going to go up here, and if I draw this particular length, the right triangle, let's call this E prime. So from the triangle BE prime D looks like this, 4, 1.2. So the angle between those things is 16.7. So this angle is 16.7 degrees. That's tan inverse 1.2 over 4. Now this angle we already calculated. If you look at the triangle BE prime E, that looks like this. This is 3, that's 4. So this angle is 36.87. And this angle is also 36.87. So in this case, because we have so many angles and we don't want to make a sign error, I'm going to actually list all the forces. So I have FBE at minus 36.87, or I can also write FBE at, let's see, 360 minus 36.87, 323.13. That's one of the forces. Then I have FBD at 16.7 degrees. Then I have FAB at 180 plus 36.87, 216.87, which is minus 15 at 216.87. Notice that whatever number I get, that's what I get. The other one is 0, so I don't care. The summation of all the forces in the x direction equal to 0 will give me, let's see, what does it give me? FBE cos 323.13 plus FBD cos 16.7 degrees plus minus 15 cos 216.87 degrees must be equal to 0. Then sum of all the forces in the y direction equal to 0 gives me FBE sine 323.13 plus FBD sine 16.7 degrees plus minus 15 sine 216.87 degrees must be equal to 0. So if you calculate these things, you should solve these two things. Let's see. 323.13 cosine. 0.8, so I get 0.8 FBE plus 16.7 cos. 0.96 FBD, 216.87 cos times 15 plus 12 must be equal to 0, and then I will get 323.13 sine. So 0.6 FBE plus 0.29 FBD the last one is 216.87 sine times 15 plus 9 equal to 0. If you solve these two things, you will get FBE equal to minus 0.714 kilonewtons. FBD is minus 11.93 kilonewtons. So again, we have now solved more. And the point which I wanted to make here is the fact that by symmetry, whatever happens at this point at A also happens at that point. So I get 12 1 minus 15, 12 1 minus 15. If that's 0, that's 0. This is 12, that's 12. If now I also have this bar force FBD is minus 11. So this one will be minus 11. Then let's see. This one will be, this one is minus 0.714. That one is minus 0.714. So the only thing that's left is this bar. So I'm going to go to joint D. Let us see. I've written some nonsense. I'm going to erase all this stuff. So let me go to joint D. I'm going to draw the free body diagram of joint D. That's 11.93. By symmetry, that was 11.93. The force here was 6 kilonewtons. This one is FDE. I don't have to do much. You can just sum all the forces in the y direction. If you sum all the forces in the x direction, and remember that this angle is 36.786, this are 87, this angle is 36.87. So it's pretty easy to calculate that summation of all the forces in the x direction will give you 0 equal to 0. That's good. Summation of all the forces in the y equal to 0 should give me minus 6 minus FTE. Those are both negative. So minus FTE, then minus, so remember y is positive this way, x is positive that way. And we have done this so many times, so I'm kind of going fast on this because I want you to see how I got this. So without wasting too much of your time, so I'm kind of going fast on this. So I get minus 6, that's done, minus FE, that's done, these two things minus 2 times minus 11.93 sine 36.87 equal to 0. The 2 times comes from the fact that I have one contribution from this side, one contribution from that, and 11.93 is that number, sine 36.87 is that number. So you can calculate FDE will turn out to be 0.856 kilonewtons. So now we have everything. So let's kind of summarize and see where we are. So for us to be able to summarize, I want this figure. And I'm going to redraw this figure. Ah, here it is. Great. I'm going to draw it large so you can see. There. So this was 12, that was minus 15, this was 12, that was 12, that was 12, and let's see, that was minus 11.3, so in 11.93, so that was minus 11.93, this was 0.857, and that was minus 0.714, this was minus 15, that's 0, that's 0, so this is minus 0.714. So what I want you to observe is that some of the bars have positive numbers and some of them have negative numbers. What it means is that there are some bars that are in compression, that is, they're pushing against the joints. Some of them are in tension, they're pulling on the joints. So let me mark those things which are under tension in blue. So this bar is under tension. What it is doing is it's pulling the joints C and E. This bar is in tension. 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 Then this bar is in compression. That's in compression. That's in compression. That's in compression. That's compression. And that's compression. So if this was made by your ball and magnet system, you can see that the bottom of this truss, the joints, the bars AC, CE, EG, and GH are under really heavy tension. They are under 12 kilonewtons of tension. So what's going to happen typically with your truss is that one of these bottom bars is going to fail. So what is going to happen is either this or this or this or this are going to fail because they all have the same load. Which one fails depends upon exactly which of the magnets are slightly weaker. But what it allows you to do is, without actually testing the bars, you can figure out, hey, if the thing is going to fail in tension because the ball and magnets are going to separate, it's going to be on the bottom row. So this gets you an idea of how to calculate the internal forces. You systematically, so just to give you a quick overview, we first calculated the reaction forces, these two. Then we went to this joint and we calculated these two forces. Then we went to this joint and we calculated these two forces. Then we went to this joint and we calculated these two forces, this and that. Then we went to this joint and then we'll calculate that force. So the trick is we slowly systematically go through all the other bars we figured out by recognizing the fact that this one half of the bar was a mirror image of the other. The point about doing this calculation is to start at one end. You never start in the middle. Always start at one of the joints. I mean, either the pin joint at one end or the roller joint. It's better to usually start at the roller end. Solve two bars at a time. Notice at every stage we had two unknown forces. That's what allowed us to do this whole problem. So as soon as you see a joint, that's why we went to joint C and not joint B, because joint C had only two unknown forces. Until we solved joint C, then we were able to solve joint B. If I started with joint B, I would have too many forces. I hope this helps you do this problem. There's another problem exactly like this solved, but without annotation, that is without my voice on it, in the PowerPoint slide which I'm going to put up. I hope this works. Thanks. Bye.